It's the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 54, where today we are going to be talking about experiments that changed the course of history. Of physics, of course, of science.
That is a little bit dramatic.
Yeah, of course. I mean, we
just...
have to make it dramatic for the audience expects drama. You guys
it's
expect
just
drama.
Be very cool experiments
Yeah.
in general, and also maybe kind of not what you're expecting.
Mm-hmm.
Because when you think of experiment, you think of, okay, there's a setup, you got equipment, you try to measure something, okay? Mm-hmm. But we are going to dive into some thought experiments where we are going to be living in a perfect world where our tools are perfect, but we're going to analyze, maybe some situations where we need thought experiments to kind of really understand concepts behind
thought experiments are super important, because I think a lot of them lead to theories, very important because a lot of things, like, sometimes you just can't really perform in reality, right? Like the famous Einstein thought experiment of the train, the light with the mirrors in the train, the classic way of explaining relativity.
I don't think that experiment led to a theory.
No, but the idea that it has, the idea of the theory, the idea of the thought experiment leads you to understand a lot about what the theory of relativity is and what it means. So it's like it's part of like his postulates and is the ways he understood relativity. So
and in this case,
so thought experiments could be really important. Sorry.
Oh, are we hinting towards a special relativity part 2?
I think we need to. I think we really do. We've been mentioning it back and forth, but then I think this one took triumph. The reason why, though,
is because we don't really know what to say. We've already gone through a lot of the concepts in the part 1, and so we'd have to do kind of a little bit of research, figure out what we haven't said and what we could say. That would be like something new, because we don't want to repeat the same thing.
Also, someone actually recommended... See, again, we do your recommendations just a long time later, because I think someone recommended like a history of physics episode, but instead of talking about people, talk about experiments.
I'll actually try to find that.
Yeah, so maybe if you can find that, that would be really cool. But so someone emailed us and said, hey, why don't you do this instead? And we put it in the back burner, never really did it well until now. So I think it's a really cool idea. And instead of just talking about, it's just 2 or 3 experiments, we're going to talk about some experiments that kind of reshaped science.
Okay, so this was actually Jeremy Bayer who sent us an email.
Oh, wait, he's commented, I think.
So he sent us an email saying that we should do a history of physics, but where we pick experiments. Mm-hmm. And I don't think this is going to be... I guess we can make this part of the history of physics.
No, not really. Not really.
It's historical.
But we're talking about... This is like a 1-part, I think. No, actually, this doesn't have to be a 1-part episode. We can make...
No, it doesn't have to be.
Because we can just think... Because there are a lot of experiments in history that have... So maybe we can talk about the name later, but we can, I think about something apart from history of physics. Maybe like a new name, a new series talking about experiments that changed the course of history. Something like that. We'll think about that. We'll give it a thought.
For sure.
For now, just experiments that changed the course of history. Mm-hmm. So let's get into it.
Before we get into the podcast, we do have our...
I forgot about the news segment.
Our little news segment here. So first of all, we have passed 85,000 downloads. So close to 100,000.
So close.
So
we can taste it.
And back when we were, I think we had like 20 episodes out. Mm-hmm. I told Rayhan, I said, we're going to hit 100,000 before 100 episodes. And Rayhan doubted me so bad. But as always, I'm correct.
I'm like, there's no way we're going to hit 100,000 by 100 episodes.
As always, I am turning out to be right.
That way.
And I don't think, I know episode 1 of the podcast is nearing 10,000 downloads.
Really?
Yeah, and so we're not exactly at 1,000 episodes or 1,000 downloads per episode, but it's
Yeah, it's very skewed. It's really weird because like a lot of our earlier episodes are really nice, but then actually it's not even that. It's kind of like picking up slowly because as we're growing now, like a lot of people are getting to know our recent episodes, and then a lot of these people are going and watching our original episodes. So those guys are growing, but these guys that we're releasing now are growing as well, just faster, right? So it's all like a whole distribution, if you think about it, like a statistical distribution. So we can actually think about, where is our maximum. But yeah, I mean that's the idea. So we also have a quick Spotify update on our Spotify followers. We have hit or passed 6,500 followers now. So yeah, that's a pretty big, I don't know, it's just a mark. I think every episode we're just gonna like try to announce our news, alert you guys about what's happening with the podcast.
So yeah, I think we can definitely get to 10,000 very soon. If you are listening to this episode right now on Spotify, make sure to hit that follow button. We are trying to get to 10,000 followers. Also, if you're watching this on YouTube right now and you have a Spotify account, make sure to check out the audio versions, because the audio versions are actually a little bit different from the video versions, because we don't edit the video versions at all, because it would just be difficult with the video and the audio and all that stuff. But the audio, it's a little bit easier because we can just like cut parts out. So anyways, the point is, make sure to subscribe to us on YouTube, because we are almost at 500 subscribers on YouTube. Yeah, so other than that, you can ask us questions, you can leave a comment. You might be asking, why should I leave a comment? Because of the comment of the week, which this week comes from divisible by 0. They say...
Wait, sorry, yes. Who said this?
Divisible by 0.
Oh, that's the name of the account?
Yes.
Oh, okay.
And they say, yes, I love how the episodes are getting longer and longer as they go. Much love, keep it up. Not the first comment, but I'll take second place.
Hey,
well,
that's nice.
That's hold nice. First place because you are the comment of the week this week.
Oh, he got it.
Make sure to leave a comment on this episode. I think we should start taking just comments from the actual episode. Instead of just picking comments
because first
from,
when we
clips,
originally started the comment of the week, we also weren't getting that many comments, so I think you guys are commenting more because of the comment of the week, which is nice. I mean, it's working, right? So originally we were just picking random comments, like some were emails and stuff like that, and I think we will still pick emails. Like if you guys send us like really cool emails, like we're still gonna pick them for the comment of the week, even though it's not a comment. But so it doesn't have to be that, but like we're not gonna pick like a comment from like 20 episodes ago unless it was made like in the same week, right? Because it's comment of the week. If we got anything in that week, we'll talk about it.
I think from now on, make sure to leave your comment on YouTube in the comment section of the full length episode, and we'll pick comments from that comment section.
Boom.
Not like the clips or Instagram or anything.
I mean, we can, but like, it would be preferred. It would be easier for us.
So
sure.
Yeah. So let's get into this episode.
Let's get into it. I think we should start with... Okay, so before we get into like the experiments that truly shaped like history, where we talk about the past experiments and, like some experiments we're, I think, going to get into that happened in the 1700s, the 1600s, and these guys were just, geniuses all the way back then. So it's really interesting to think about. But before we get into the past, I think we should talk about two very monumental experiments that took place in this century. So basically in the 2000s, right? So the one that happened actually very recently, which is in 2015, 2016, the very famous Ligo Experiment. So I think we have spoken about LIGO before. I definitely remember, where it's basically a gravitational wave observatory. It's called a Laser Interferometer Gravitational Wave Observatory. Stands for LIGO.
I think we talked about it in the interview with Dr. Steinberg.
Yes, I think we did. I think we did talk a little bit about that. Yeah, it's a really cool facility. And, they have huge arms and stuff to basically detect gravitational waves. And in 2015, almost, and this is a little weird, I was talking to Parker about this before, almost exactly 100 years after Einstein's general relativity paper, which was in 1915, they discovered these gravitational waves in 2015. And I just find, it's just a little eerie.
Which is actually like one of the predictions that has been confirmed, right?
Mm-hmm.
Because the theory of general relativity has several predictions, and gravitational waves is one of them.
Mm-hmm.
And so 100 years later, approximately, it was actually confirmed. Now, some things have yet to be confirmed, like white holes. We have not confirmed white holes. We have confirmed black holes, though, recently with the images of black holes. But even before capturing an image, theoretically, or I guess experimentally, we knew that black holes already existed because of the mass and the kinematics of galaxies around the centers. We could infer that something really, really massive and, not that big, quote unquote big, was lying at in the center.
Yeah, and gravitational waves are so important because, remember, Einstein predicted that basically he said gravity doesn't even exist. It's not a force, it's just basically space-time, right? And if you guys checked out our episode 51 with Dr. Saeed Rastagu, super cool episode, where we were actually talking about how gravity is not a thing. It's not even, it's just a consequence of space-time curvature. So gravitational waves are not gravity, it's just space-time moving up and down. It's basically just oscillating space-time. So I don't know if we spoke about how they did the experiment, maybe just a quick rundown. So basically LIGO has two arms that are perpendicular to each other. And if a gravitational wave, in this sense, were to pass by Earth, it would be moving in one direction primarily, right? So it will be moving so remember, because gravitational waves is space-time that is moving, it's literally stretching and compressing space-time. That's space, basically. So when it comes to one of the detectors, it will shrink one of the detectors, one of the arms, more than it does the other, right? Because one is perpendicular to one and it's only going in one direction. So it's going to shrink one more than the other. So the light that is actually being reflected off of these arms will take different times to reach the photodetector.
Okay, but think about this real quick.
Yeah.
I don't know if you have the answer to this, but what if the two perpendicular arms are set up in a way as if they were the two top sides of a equilateral triangle, and then what if the gravitational wave comes in transversely, right? So then it would kind of affect the arms by the same amount. So how would it work?
No, but this is perfectly perpendicular, right? So it's literally two different... You can think about it if you're thinking about X and Y, right? They're two different dimensions. So you're looking at two perpendicular dimensions. You're literally looking at two different directions. One that goes north and one that goes east.
What if it's like this? This isn't a very good audio description.
For the audio, yeah.
Okay. Okay, imagine it's like a tent, right? The two sides of a tent.
I understand what you're saying.
And then it sweeps out vertically across. So it kind of affects each arm by the same amount.
I kind of understand what you're saying, but that won't necessarily be the case because of the speed of light and how fast these detectors are really detecting this change. So the moment the gravitational wave comes and shifts one of them, again, I'm probably, this is just my guess, obviously, I don't know this, but my guess is the moment the gravitational wave comes and shifts one of them, the other one is still going to be in sync. So the light that's received at the photodetector for that split second, which obviously it can account for, is because...
So I guess now you can kind of comment on the accuracy of these detectors.
Yeah, I was actually just going to say, a really cool thing about LIGO is that maybe I can pull the quote straight from the thing, but basically, wait, where is it? Do I still have the quote? Oh, no way. Oh, it's right here. It's right here. Sorry guys. I'm looking for... Okay, basically he was saying the accuracy of LIGO is like measuring the width of a micron. So basically like think about the width of a human strand of hair. So a micron, basically, a micron thick. Measuring a human hair at the distance from Earth at Alpha Centauri, which is about 4 light years away. So the accuracy is as good as seeing that piece of hair 4 light years away. That's
extremely
how accurate this thing is.
But, this is accurate in terms of human tools, right? Because we're never going to need that type of accuracy for measurements locally here on Earth.
Of course. This is just for extraordinary experiments, right?
But when you think about astronomical scales, this is actually, quote unquote, not that accurate.
4 light years?
Right? 4 light years is not that far.
Oh, nothing. It's
right?
absolutely nothing.
Exactly.
It's nothing.
Exactly. So that accuracy, when you're trying to measure something that is, 20 billion light years away, it's not going to translate as well as, something that's 4 light years away.
Another really famous experiment that was kind of conducted in the recent century, I guess this was an experiment. The Large Hadron Collider in CERN detected the Higgs Boson for the very first time. Now, for anyone who, and this happened around in 2012, right? Yeah, around it, because when I searched online, it said 2011 to 2013. And I'm like, it happened so recently. Why don't you know that? But I'm pretty sure it happened in 2012. But the interesting thing about the Higgs boson is that it was proposed by Peter Higgs, hence the name, and his colleague Francois Englert. But I guess Peter got the credit. So it was designed and it was thought of by both of these gentlemen in 1964. And they had been trying to find experimental proof for the Higgs boson, obviously ever since then, but they knew that the experimental accuracy and technology was nowhere close back in the 1960s. But then, when they opened up CERN, they tried to look for this particle, but I believe that they were unsuccessful. And then, after a revamp of the facility, and I guess a few more tries. So basically, they're just smashing particles together over here and seeing if anything gets excited enough so that they can detect them. And they detected for the very first time this particle that they had never seen before, and everyone called it the God particle that we now simply know is the Higgs boson. And the meaning behind this is because the Higgs boson is not that special because it's just a particle. What's more important is the Higgs field. The field, so much like the electric field, right? Like an electron, we were talking about it, and like an electron is an excitation of the electric field. So in the same way, a Higgs boson is an excitation of the Higgs field. So if you're imagining, the Higgs field is basically everywhere in the universe, and it is what allows particles to gain mass. So basically, in other words, when particles interact with the Higgs field, they are restricted from traveling the speed of light. So this actually answers the question for why massless particles can travel at the speed of light, because they don't interact with the Higgs field. And because they don't interact with the Higgs field, it's basically a smooth transition, and they can travel at this maximum possible speed.
And something that's pretty cool is that we actually interviewed a physicist that worked on the team that discovered, or experimentally discovered / found the Higgs boson, Dr. Pekka Sanervo, which was episode number 4. I think.
I love that gentleman. He was one of my professors for one of my classes. Amazing guy, super super cool, because he was teaching me a very low level physics course. Sorry. A very low level physics course, right? And I'm like, okay, this guy's probably, not done that much.
That is not true.
Blown away. This guy has done everything you can imagine, man.
And something that's really awesome is that, really good, intelligent physicists always have the best analogies for things, right?
Yeah.
You ask them like a complicated question about some complicated theory, and they're like, okay, think about it this way. And then suddenly, it makes a lot more sense in your head, even though you haven't studied the actual details of it. And I think we talked about, we asked them a question about topics in physics that just can't be explained, not even topics in physics, just topics that come up in our physical universe that can't be explained by physics. And he brought up the example with mixing milk in coffee, right? And how you just can't, like, no matter how much like experimental setup you have and how accurately your devices are, after a certain point you will just not be able to exactly model how liquids just disperse, because it does have to do with turbulence, which we have talked about,
like how the
with,
milk basically flows into the coffee is what you're talking about, right? Yeah,
and we
like how
talked
it
about turbulence also
disperses. Yeah.
with our first year physics professor, Paul.
Oh, wow, wait, we're blanking.
Wait, Doctor. I know his name is Paul.
We're actually blanking right now.
This is crazy.
Wait, no, Stephen Julian and Doctor Julian
Paul.
and Doctor.
It's Paul.
No, Dr. Julian and Dr. Wait, there's no wait. Dr. Julian.
Paul
Sorry,
Kushner.
guys.
Paul
Kushner. Dr. Kushner.
Yeah.
Oh my, that was so. Oh my, this was really sad. Well, sorry for that quick. Oh wow. Okay, Dr. Kushner. Yes, he was a very, very, very cool guy. We were talking about fluidity, like flowing and stuff with him as well. Also with Tom Rock's math. With Tom Crawford, we were also talking about fluid flow because he actually got his PhD in fluid mechanics and fluid flow and stuff like that. So yeah, so that's where, all of these different parts, like, become really important. And yeah, so the Higgs field with a really cool experimental result back in 2012. I think now we can move on to the
So
true historical experiments.
I'd like to take our listeners now on a trip, a
Oh.
blast to the past.
I love this.
And this is my favorite thing to talk about because I am truly intrigued by history itself. Not even the history of physics, just history in general. Like, how do you even live in a time where you think the world is like Europe, Asia, and Africa? You do not even know about the extent of where you live, right?
The universe.
This may be a little bit dramatic. I'm not going that far back. I am going
People
back.
lived and died. I'm sorry to cut, but I'm just thinking about this now too. People lived and died. So their entire life not knowing anything about what they were living in, what situation they were in, understanding why. I mean, I guess we don't know why now either, but like just understanding where we are.
Yeah, and this might be a little bit of a sidetrack here, but I was thinking about this. I don't know when, but I was thinking about, let's say this is like 70,000 years ago. You're a hunter-gatherer, just, collecting berries and hunting animals, right? You don't know anything about anything, right? You don't know anything about, well, okay. You don't know anything about, like, world geography.
I mean, you know how to skin an animal or something.
Yeah, you don't know anything about, like, actual, like, modern physics or history.
I mean, obviously, yeah. Like, a guy in the past wouldn't know modern physics. Like, I mean, it's obvious in the word modern.
Okay, but all I'm saying is that you don't really know anything about anything, okay? And you know absolutely even less, right, about space and the Earth itself and where you're living, right? Like, you have no way of knowing that your entire life, like where you live, is just infinite. Like, nothing tells you that is not the case. Like, if you were to just walk in one direction, like it's like a Minecraft world, it just never stops, like, generating, right?
Mm-hmm.
And so if you try to put yourself into that perspective, then it kind of makes sense to believe that you are at the center of the universe, right?
Sorry, that was a quick cutoff of the internet right there. You glitched out.
Okay, so listen. You have no reason to believe that you are not at the center of the universe.
Oh, that's the argument that everyone lived by. And I think, a lot of people, I mean, if you think about the universe as an infinite thing, obviously, like 500, 600 years ago, or you're not probably even thinking about the universe. You're just thinking about.
I think that's not far back enough.
Okay, I get
500 years ago they had.
Okay, I guess 500 years ago that's true. But yeah. I'm saying like 1500 years ago, let's say 2000 years ago, people really didn't understand the vastness of the universe, right? I mean, again, we also just understand our observable universe right now, but people really didn't understand the true reality of what we're living in. Right?
Yeah, that's true.
So, and the idea is that if they couldn't understand it, I mean, we simply have an idea of, like, for example, when we say 95 billion light years, it's 95 billion light years long. Like, what does that mean? We can't really understand it.
It's just a result to some like models that we've come up.
What they were doing 5,000 years ago, 2,000 years ago is not that crazy, because if you think about it, like, we don't really have a concept of distance right now. And we will probably never, with our size, like 2 meters long, like that's nothing. We will never truly understand the concept of distance scale in the universe. So it's not a very big difference between someone 600 years, like 6,000 years back, 5,000 years back, to someone now.
Although with what you said,
so just one more thing, because in our frame of mind, we are the center of the universe. If you think about it,
I feel like 70,000 years ago, life felt a lot more like a video game. You just spawned in and then you just like lived and then like it was over.
You just do your stuff, man. You just do your stuff. You have no idea what to do. You never really thought about anything
like
you do you.
Outside of that. But
that is I think the pinnacle, the definition of you do you.
Okay.
Just. You do you, man.
I want to comment on what you said earlier, though, about with our size as being like around 2 meters. I have an issue with that, in that I don't think that like massive life forms could really exist. And think about it like this. If a planet was so big, so massive, that to be able to like hold yourself up on 2 legs, you would need like massive bones, massive muscles, right? Biologically, you would have to be a huge creature to be able to sustain the gravitational pull. No, I'm not saying we should
be big, because we can never truly be big biologically speaking. I'm saying that's the restriction, though. That's the whole restriction.
Okay, I get it, but just listen. I'm saying that we're never ever gonna find like intelligent beings that are like 20 times bigger than we are. At least,
I can see that. Okay, yeah,
the universe is infinite, so I don't actually know. I'm just guessing, because here's the thing. First of all, to be able to live, to be able to be 20 times bigger than a human and to be alive, you need a lot of food, first of all, which means you need a lot of resources and a lot of things, okay? Also, let's say for like biological reasons, the reason why you have to be so big is to like fight. I think this argument might make zero sense, but bear with me. You need to fight like the gravitational pull of a massive planet, right? But turns out that a planet can only be so massive before it turns into a like, what are they called? Like a brown
dwarf?
Like the planets that are in between stars and like actual planets. Like, I'm pretty sure Jupiter is actually like in between a brown dwarf, let's call him. I think that's what the actual
brown
name
dwarf
is.
is the term for it.
I think Jupiter's actually like in between a brown dwarf and a planet, because it's so massive that it's actually like almost there, But anyways,
I mean, there are bigger planets, but yeah,
but all that to say is that you can never support life on a planet after a certain mass, right? Do you get what I'm saying?
Yeah.
Do you get what I'm saying?
You glitched out after mass. I don't know what you said after mass. Sorry.
After mass, I said, do you get what I'm saying?
Oh, yeah, I understand that there will be people, but I don't know. I mean, you're talking about like individual people that are huge. Like, I don't think that's something that I was even talking about. Like, I'm just saying, I guess that's a question
Not even
that you can
people.
ask. Like, or yeah, people, well, some biological
Anyways.
creature, like some creature. Anyways, not that any of this has anything to do with what we're talking about.
Let's just skip over this right here. If you have any
That has
opinions,
nothing to
please
do with
let
what we're
us
talking
know,
about.
and we will, we might get back to this idea in the future. So I was gonna go back into the past and talk about something very simple, but very remarkable and a little bit counterintuitive. Okay, so it's said, right? The tale goes as such: Galileo was sitting in church during mass, and he was looking at a chandelier because he was bored. He looked up at the chandelier and it was swinging, okay? And as we all know, if you have some type of pendulum, you start it at some height. Over time, that height is going to, like that maximum height is going to decrease until it comes to rest, okay? But he noticed that the period seems to stay the same all throughout the pendulum's lifetime. And so back in the 1600s, they didn't have clocks or anything like that, so he used his pulse to actually time the period of the pendulum. And he saw that, you know, even if the pendulum was swinging wildly, the time it would take to go back and forth would be the exact same as if the pendulum was just swinging very lightly, right? And you know, intuitively, if you were to ask like a non-physics student, non-math student, like, what would you expect? Well, they would say, okay, well, if this pendulum is swinging to a very high extent, it's moving very fast, and so the period will be short, and then, the period will be short, and then if it's moving slower, the period will be longer. But, you know, if you model this mathematically, you'll actually find that the period of a swing only depends on the length of the pendulum, not on the mass, and also not on the starting height. And so you can actually interchange the masses, you know, you can interchange the, like, how high you start the pendulum at, and the periods will actually stay the same as long as the length is the same.
But do remember, like, the
so
height...
that was kind of a...
Sorry, but do remember, like, the height from, like, the surface of the Earth, it will change on it because it depends on G as well, right? Like, small G.
Okay, I'm talking
like
about
gravitational
pendulums
acceleration
here at the surface.
Okay, yeah, so
at
if you're
the
just,
surface
obviously,
of
if you're
the
just
Earth.
talking about the surface, then yeah, it's not really going to make a difference. But, like, if you're doing it on or, like, at sea level, or if you're swinging a pendulum, I don't know, up on a mountain, for example, like, yes, there will be a very slight change. Obviously, very microscopic.
There will be
But
the ever so slightest
But
change.
there will be a change. That's the point. That it depends not only on the length, but also on G. That's the whole thing.
Mm-hmm.
Right?
And this idea will actually come up in an experiment that I have to explain later on. But yeah, this little pendulum pulse timing experiment is, you know, he figured out a physical property about pendulums and their periods just by using his eyes and his pulse. Turns out he's absolutely correct. The periods do not change whether you're high, low, heavy, light. It only depends on the actual length of the rope.
Man, and the amazing thing about all of these things that we're going to be talking about today, because there are some really cool experiments that we're going to dive into, is that these guys are literally just people, just regular people, just had a thought in their head.
They have creative ideas.
They're just regular people like you and me, have a thought in their head. They're like, hey, let me just try and do this, and it just revolutionizes history. Like, I just think that idea, the concept of you just sitting at home and thinking about something, like, you know, for example, when, like, Newton was sitting at home quarantining from the plague at the time or something, right? Like he just discovered. Wait, what did he discover when he was sitting at home? Was it
Calculus.
was it calculus or was it? Yeah, it was
Yeah.
calculus. Okay, so it was calculus when he was just sitting at home. See, something like that. It's just amazing.
And physics itself is actually the wildest detective
Mhm.
situation here. The clues are under your nose, right? You have all the clues available. Well, you don't have all the clues.
Yeah, you
but
really don't have all the clues. You're trying to
but
find a lot of the clues.
you have a lot of clues. A lot of clues in front of you. You need to actually come up with ways to piece these clues together and come up with different explanations.
Mhm.
You know, for example, how do we explain the physics of stars, right? How do you even start to analyze stars? It's not even like we're close to our sun. Relatively, we are close to our sun, but we are still hundreds of millions of miles away, or 100 million miles away. So how do you know what's going on inside the star if we're so far? Nevertheless, you know, every other star in the universe. Well, turns out that we are really good at using clues and using tools to piece these clues together. For example, looking at the spectral properties of elements, burning elements, which, you know, stars are just burning balls of elements at the end of the day. And I do think spectroscopy is one of the most revolutionary tools that we have
Spectroscopy
in astrophysics, right?
Is insane.
Absolutely,
I think not
crazy.
only in astrophysics, in literally anything. Because
No, I know,
spectroscopy,
in
you can understand
anything.
the composition of a lot of different things, just in general.
I think more
not only-
specifically, though, we use spectroscopy so often in astrophysics to determine like the composition of stars, to determine the redshift of stars, which has to do with their velocities, or sorry, the redshift of galaxies, which has to do with their velocities, and actually the redshift has to do with also their age, which we can actually touch on in a further episode of astronomy part 4
Yeah, might have
if
to
you
do
guys
that,
are
too.
interested. But yeah, you go ahead, Ray, with your next experiment.
Yeah. So moving on to another fundamental experiment in the history of science. We have Ernest Rutherford's gold foil experiment. So if you guys have taken like a chemistry class in grade 11, grade 12, you might have heard of the gold foil experiment, which basically sort of proves that the atom is not the smallest part of the universe, is not the fundamental piece of nature. Because originally, when atoms were, thought of or devised, like the meaning of atom in Greek means indivisible. It means uncuttable or something like that, right?
Which is false.
Sorry?
Which is false.
Oh, of course. Like the statement is false, but
Yeah.
the atom means indivisible.
Yeah.
And Rutherford was like, well, no, I don't think so. I think the atom has a central part to it with things flying around, right? With these negative charges flying around, basically. So his idea was to send positively charged particles, so basically just the nucleus. Again, in that time, they didn't even know the nucleus existed. So they just charged, I guess, a particle and they sent it through. The point being that there was a gold foil that was simply straight in front of that laser, let's say. And there was a screen all around that gold foil, nearly 360 degrees all around that gold foil, kind of like almost like like circulating it almost, except for that, obviously, that one slit where the laser can come in from.
Mm-hmm.
I mean, again, it's not actually a laser. Laser is the wrong word for it, but I'm just using it because a lot of people can understand, like, oh, it's okay, it's a light beam, right? So it's like charged particles, basically. It's not even light, really. So the idea is that if an atom is an indivisible element, then then all of the particles from the charged beam would pass through the gold and end up in the same spot.
Actually, that's not the reason. Like you said if the atom is indivisible, then it would actually just pass through. But the actual reason is because before this experiment, they thought that atoms were like plum puddings, right? They were like positively
the plum pudding
charged.
model. Yeah.
Like positively charged particles inside of like a negatively charged pudding type deal, or maybe it was the opposite, like a positively charged pudding with negatively charged particles inside of it. But anyways, the point was that these packets were neutral because it was positive and negative. They would just cancel each other out and everything would be neutral. So if you were to send positive particles through the gold foil, there would just be no electromagnetic interaction whatsoever because everything is neutral, so it would just pass straight through. But what they saw was that there was deflection, reflection of these particles, which actually was proof that it's not these neutral packets, but they're separated in positive and negative, and that these positive particles would sometimes come close to the nucleus, which would then you would have an electromagnetic interaction there, which could deflect, reflect, and deviate the paths of these particles.
So basically what they observed was that all of these particles of this beam were not all traveling in a straight line and appearing in the same place that where they left. Instead, they were all deflected around this circle. And the percentage and the amount, per 1,000, and basically understanding the percentages of where each would go is also obviously written up in a very concise manner. Not that I'm going to start spitting it out right now, but the idea is that there is a probability for any for this alpha particle to go anywhere depending on what part of the nucleus it hits, where it hits, how it interacts. So many factors, so many factors. And again, the moral of this story, like the moral of this experiment, is that it kind of sort of proved or helped prove that the atom is not an indivisible element. It instead contains smaller subatomic particles, hence the name. And I believe first we only understood the nucleus and electrons before decomposing the nucleus into neutrons and protons, right?
That's right.
And remember, like, the idea behind all of this is simply to have a good understanding of your situation. So he understood what he needed to do to prove this experiment. And I think that's a big part of experiments, knowing how to design it. And if you guys want to check out Brilliant, they have some really cool courses on experimental design, how you can, think about experiments and how you can set them up, the procedure, the hypothesis. It basically has the whole package deal where you can learn about some different concepts. For example, I'll just pull some examples out. It has a cool course literally called experimental design, one called data collection, another observation versus experiment. So it basically gives you a good idea of all these different ways to think about experiments, right?
Which are all crucial parts, by the way, because experimental physics is not just, you have data and you analyze it, right? It also has a lot to do with the actual setup of the experiments, the tools that you're using, the uncertainties, how you collect the data, and then how you actually analyze the data to produce conclusions.
A lot of this, again, stems down back to thinking about the experiment, right? Like how, you would need to know the material well enough to truly perform the experiment. And well, Brilliant helps you do all of that, right? With its vast amount of courses on all of these different topics that we're talking about today. A lot of these experiments we can actually see. There's directly spoken about on Brilliant, so it's really cool. And I think they also, they still have them, and we keep talking about them. The daily challenges, really cool challenges. Parker and I do them sometimes. And it's just fun to, give your mind a little spin.
For sure. Yeah. We always advocate for the interactive style courses where you can actually learn and then apply your knowledge. And so for the first 200 listeners to click our link in the description. Make sure to click that link. You will get 20% off your premium membership. So make sure to click that link down below. It's brilliant.org/MPP, Math and Physics Podcast. So yeah.
That's it.
Also, I wanted to actually transition into the quantum world. Because we all know how magnificent the quantum world is.
Beautiful, absolutely.
And I've actually recommended this book. I've recommended this book quite a number of times before. It is Quantum, the Great Debate About the Nature of Reality by Manjeet Kumar. What a fantastic book. And he talks about actually thought experiments that Einstein actually came up with to go against the ideas of Niels Bohr, who agreed with Werner Heisenberg, who came up with the uncertainty principle. Okay, and there are two versions of the uncertainty principle. The first one is that there is a lower bound to the product of your uncertainty in the position and the uncertainty in the momentum, meaning that you can't know both at the same time. Also, analogously, there is also a lower bound on the uncertainty in the energy and the uncertainty in time. I'm going to talk about two experiments that actually Einstein came up to say, hey, look, here's an experiment that would break this uncertainty principle. Therefore, you're wrong, and we need to think about a better theory. Okay.
The uncertainty in time.
So first of all, this is called the Einstein's.
Sorry to cut you off, but the uncertainty in time thing I think is really cool because thinking about like position and momentum, like since we're observing them, since we're measuring them, we can visualize an uncertainty. Like, okay, this is 5 meters away, plus or minus 2 centimeters. So we can understand the idea of uncertainty. But when we're talking about time, right, it's a very interesting thought because even when you're measuring time, you can have an uncertainty with that. And what this implies in like future stuff, like I don't know if we're gonna talk about like go into how that implies like, you know, quantum fluctuations and all that kind of stuff. So that uncertainty in time argument I think is a really cool uncertainty because it implies a lot of heavier things. Anyways, you can continue.
The uncertainty itself is cool. But yeah. So the first one of these thought experiments is called the Einstein Slit. And he says, okay, we have like a double slit situation here. And so we send a photon through a double slit, but it's a little bit modified. We actually hook up like a spring or some kind of device that can measure the deflection of the photon. So if the photon goes through the top slit and gets deflected downwards, then we would see the spring like compress because the photon would push it upwards. Or if the photon would go through the bottom slit, the spring would elongate. Is that
Stretch.
the word? Stretch.
Yeah.
Right.
Stretch
okay.
and compress.
Yeah. So the spring would stretch, and then from like from grade 12 physics, you would be able to work out the momentum of the photon based on the spring constant and all that stuff. And so he said this. He said, okay, you can measure the momentum with the spring, and then you can see the photon on the back screen. So you know where it ended up, the position, and you know its momentum. So what's the deal here? Okay, well, Niels Bohr actually went home, thought about this, and he's like, wait, did he just break the uncertainty principle? And actually turns out, no, he didn't, because the uncertainty principle is encoded in our universe.
Or at least that's what we think.
Yeah.
So far.
But here's the explanation, and I'm going to try to maybe break it down. This might not be entirely correct, but it's like
I love how you say that.
like because it does get kind of technical in terms of like the concepts and all that stuff. But here's one way you can think about it, okay? So in order to measure the actual amount by which the spring stretches or compresses, you should have like some measurement device. And one way to think about this is, imagine on like the frame of this setup, you put like an arrow, and then you have a scale on the actual moving part of the double slit, like the piece of wood, let's say, with the two slits. You have like a ruler. And then so when the spring compresses, the ruler will move with respect to the arrow that's on the frame, and then you'll be able to actually tell by how much the spring compresses. Okay. In this situation, you would have to be able to see, right, the scale. But in this thought experiment, you are sending one single photon through the slit, okay? And you can probably imagine the momentum transfer from the photon to the spring apparatus here is going to be very small. In fact, so small that even the act of shining light, which would produce more photons onto this apparatus, would actually disturb the spring. And by like you're trying to measure the isolated event of one photon going through a split through a split. Why did I keep saying split? Through a slit. But in order to tell the exact amount that by which the photon transferred its momentum, you'd have to be able to shine a light to be able to look and see by how much the spring compressed. But that exact act of observing would disturb the spring, because you're sending more photons onto the apparatus.
There's no way Einstein didn't think about this, though, because I think this is a pretty... Because this is actually called the observer effect in quantum mechanics. Like, this is a very famous thing that you just spoke about, like how people think that, by looking at something, you disturb the quantum system. It's not because you're looking at it. It's because to look at something, it requires light. And when the photons bounce off from the experiment, you're inevitably, messing with the experiment. So that's actually called the observer effect. But I'm like, there's no way Einstein didn't think about that. This guy, man. Freaking genius. You don't think about that?
I think the argument is actually a lot more subtle. Mm-hmm. And there's a lot of... Yeah,
there probably is something pretty complicated, because it does sound like something that could get very complicated.
There are like a lot of technicalities that even I don't understand. Mm-hmm. I just kind of read through it and I say, oh, that's cool. But that's just kind of one way to think about it. Like, even the act of trying to observe will add uncertainty, right? So Einstein is claiming there is zero uncertainty in the position, zero uncertainty in the momentum. Well, it's like, okay, well, if I want to even look and see what is the momentum, I'm adding an uncertainty, which proves that the uncertainty principle
still holds. It's all good.
Still holds.
It's all good. It's all good. Uncertainty principle never lies. At least
exactly
what we know today. Well,
I just want to talk about the second one real quick. The second one is even cooler, okay? So the second one is called the light box, or I think it's Einstein's light box, okay? And this was his argument. He says, okay, you have a box that is, you're able to suspend it on a spring, and from there you can tell the mass of the box, or however you want to tell the mass of the box. The point is, you have a device inside of the box that can produce a photon, and you also have a clock in the box that is exactly timed to a clock that is outside the box. And so, if you look at your clock that's outside of the box, it says the exact time. That's okay, you get it. So, now, here's what Einstein said. He says, we open a small slit in the box, we release a photon, and then we close that slit. Now, when we open the slit, we have the slit is connected to the clock that is inside the box. And so as soon as you open the slit, you know exactly at what time that the slit opened, and you can also tell on your clock because they're synced. Okay, so you know exactly when the photon left, and then after the photon leaves, what you do is you weigh the box, or you see how much does it weigh now that the photon left. And so the argument here is E equals mc squared. You can plug in the value for mass, and you can tell the exact amount of energy that is now in the box, I guess. And so you know the time, you know the energy perfectly well. There is no uncertainty here. So how do you explain that? How do you say, well, actually, no, there isn't uncertainty? Well, it turns out it took Niels Bohr a very long night, okay?
One night.
Thinking.
One night.
Yeah, this was during the
guy.
Slovak conference. I think in 1930. Might be the 26th one, but I think it's the 1931. The 1930, that one, not 1931. Anyways. So, here is the argument, okay, to support the uncertainty principle. And this is actually quite a physical diss, okay? And here's why. This is probably the most beautiful rebuttal ever. But here's what he says, okay? So, everything's perfectly fine. The clocks are timed together. You're able to measure when the photon leaves and all that stuff, okay? And you're also able to measure the mass of the box. But remember how I said, to be able to weigh the box, you need something to weigh it, okay? No matter how you choose to weigh it, it's going to work out the exact same way, but in this case, we'll use a spring, okay? So you let a photon out of the box. Now the spring has compressed a little bit, which means that the box is suspended a little bit higher off of the ground. And so now, everything's perfectly fine. You can measure the mass, and you can measure the time on your clock.
Wait,
at which the photon left.
Since the spring compressed, wouldn't it have gone lower to the ground?
Well, the spring is attached to
because it's on
like
the top,
a frame.
Right?
Yeah. The spring is attached to a frame, so the box would
Okay.
Okay. But here's the most beautiful rebuttal. He says, Bohr says, according to the theory of general relativity, time passes at different speeds when you experience different amounts of gravitational influence. Okay? Which means I'm getting too excited right now.
This is crazy.
This is the craziest argument. He says, which means when you release the photon from the box, the clock that's inside the box is now a little bit higher up in the gravitational field of the Earth. Which means that now your two clocks are out of sync. Which means that the time that's on the clock inside the box is different from the time of the clock that's outside of the box, which means that you actually do not know when the photon left the box.
Oh!
Hence,
he uses his own argument.
The uncertainty principle holds. The uncertainty principle holds. Always.
That's nuts.
Einstein said, here's a situation. Bohr said, I will use your own theory to disprove your idea.
That's the thing.
That
he
is
used his
the most
own
incredible
theory
diss ever.
to prove him. That's amazing.
Crazy.
That's amazing.
Absolutely crazy.
That's amazing. Niels Bohr is legitimately like, he's up there. He's up there. He's up there.
He's up there.
He's up there. He's like right up there.
How do you say, what's the word for this? Like not my favorite physicist, but like he's my like
idol. Is he your idol?
I guess.
Like,
he's
do you
my
look
idol
up to him? Do you look up to Niels Bohr? Like, do you?
Like, to me, Niels Bohr is like the most like influential modern physicist.
Even though he's not, yeah, I get that though, because it's a lot with quantum mechanics and stuff, right? Yeah. Niels Bohr is amazing.
Even though it's hard to classify like Bell with Bell's theorem, Bell's inequalities. He's actually an Irish physicist. Is absolutely very influential because he actually took a mathematical statement that had nothing to do with physics to actually prove something about quantum mechanics, which means it's actually irrefutable, right? If I say this is something about just numbers and probabilities, and you can apply the situation, you can explain the situation with this theorem here, you actually can't say no, that's not true, because it's been proven mathematically. Very
Once it's
influential.
mathematically proven, it's game over. That's it.
Exactly.
It works.
Exactly. You just can't go back.
You can't go back.
And then also Heisenberg.
Insane
you
guy.
can't really
Okay,
rank
to be
these
honest,
guys.
all the people in that picture, the Slovak conference
Yeah.
picture, I mean, obviously there are a lot of people that are not included in there that are also
Yeah.
very influential,
Yeah.
very, 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 meaningful in today's science world, but basically those guys. Yeah.
I think they were very biased with the people they invited,
Hmm.
because there were a lot of physicists and scientists that just didn't get an invitation to those conferences but absolutely deserved to be there.
Mhm.
At the same time, you can't invite everybody, so you have to make
Obviously.
decisions. But yeah.
Anyways, I mean, we're not going to get into logistics of the Slovak conference, but it is something to consider, and those guys are very smart. And since we're talking about light, I think it's a cool transition to talk about another experiment. And I think this is super cool. This is just in general very cool. This is just something that, again, you're just like, how did he even think about this? Like, it's just interesting to think about astronomer by the name of Ole Romer. So Ole Romer existed in around the 1700s, right? And this guy was an astronomer. And he accidentally solved, sort of, for the speed of light. He was the first recorded person to ever measure or to quantify, not measure because you can't, but to quantify the speed of light. Because before Romer, everyone believed that either the speed of light was way too fast to measure or it was infinite. So most of the people before that had been under the impression that it was infinite. And I'm pretty
How
sure
would that make any sense, though?
it was
it was
Descartes that
infinite?
said that too. And it was a philosopher, Descartes, that said that the speed of light is infinite. And again, I don't think they really knew enough about the Big Bang, the CMB, and none
Yeah,
of that
of
had
course.
been invented yet. So
Of course.
exactly. So I guess they didn't really have any evidence for saying that it shouldn't be infinite. Right.
Yeah.
So they could
So
have
that would
just
make
said that.
nowadays that would make absolutely
Obviously,
no sense.
obviously, zero sense. But like back in those days when you don't have any evidence for really anything, even saying it's infinite is technically incorrect because you don't know that. You think that.
Yeah.
So saying that it is infinity is wrong. Anyways, so how did he do it? So this guy was basically measuring the orbit of Io around Jupiter. So Io is one of Jupiter's moons, and he was basically measuring when Io gets eclipsed by Jupiter with respect to the Earth, right? Like when you're measuring or when you're seeing Io with a telescope. So what he noticed was actually something that you would think is obvious because of the finite speed of light that we know now, but obviously back in the 1700s, not many people really understood that yet. So what he noticed was that while he was moving closer to Jupiter, the time intervals that Io spent in the eclipse was becoming shorter and shorter. And this is while Earth was moving towards Jupiter in the orbits, right? Because Earth's in a much smaller orbit, so it's going to be catching up and moving away from Jupiter very fast, so you can have multiple measurements. And what he also noticed is that when he was moving away from Jupiter, the time intervals were getting longer. So
By how much?
exactly. So it was 11 minutes every round. Every round it was 11 minutes. From when it was the longest to the shortest, it was about 11 minutes off from the average predicted value.
That's pretty significant, to be honest.
Exactly, because also Jupiter is quite far away.
Yeah.
Right? So it's also like these small changes in like it might be like a few light minutes. Maybe not. Yeah, it's because it's more than 1 AU. So it's going to be more than 8 light minutes of difference, right? So light takes more than 8 minutes to get from the sun to Earth. So it's probably going to take a little more because, wait, what's the distance from Earth to Jupiter? It's definitely over
5
1
astronomical
Yeah,
units.
it's something like 5. So it's going to be like 40 light minutes or something like that. Anyways,
Yeah.
point that I'm getting at is that
It's actually it's 10 minutes. 10 light minutes from Earth to Mars. So
really
it's probably yeah. Because I remember seeing in a Veritasium video that
the
it would
Earth
take 20
wait,
it would take 20 minutes to send a message and get a message back.
that I believe is not okay. Those are different reasons, though. I don't think that's because of straight line. I don't know, 20 minutes, because I'm just thinking because the sun, light from the sun takes 8.5 minutes to reach Earth, and that's 1 astronomical unit. So I'm thinking, is there 1 astronomical unit between Earth and Mars?
Yeah, definitely.
Okay.
100%.
I'm in an astronomy minor. I should really know this, but hopefully none of my teachers see this.
Yeah, the distance from Mars to Earth is 258 million kilometers. So it's more than that. It's more than an astronomical unit.
Okay. So
Yeah.
we have our answer right there. Anyways, the point that this experiment is for is that he measured that Io was having a longer eclipsing period as you were moving away. And he told himself, well, the orbit of Io is not changing. Like, that's obviously pretty rigid. So what's changing is how long I am looking at it for. And that means how long the light is taking, or what I am seeing through a telescope, that light is taking from there to reach my telescope. Because remember, a star 500 million light years away, if we're measuring from a telescope, we are seeing the star 500 million light years ago. So if we're looking at it take a longer time, it's because the light is taking a longer time to get to us. So we are seeing a longer time interval.
And you can also think about this as if they were like imagine you're going through like waves that are coming onto the shore. You would be, let's say there's 3 waves that are coming towards the shore. You would be able to get over those 3 waves faster if you were going into the ocean than as if you were going towards the shore as well, because you'd have to go faster than the actual waves themselves. So, if you're going towards the waves, you actually see the waves faster than you were to see them if you're going away from them.
And so Romer postulated a calculation for the speed of light, and interestingly enough, he never did it. He postulated the calculation, but it was Christian Huygens who actually calculated the very first ever quantization of the speed of light. And he got an answer of somewhere around 210,800 kilometers per second. Now, we know the speed
Which is not bad.
Which is not,
Not
bad
bad
at all. Which we know today the speed of light is about 300,000 kilometers per second. So 210 might be like, oh, it's 90,000 less, but it could have been magnitudes more or less. Like, the accuracy is not terrible for 1700s, right? For the 16th century. So
Why didn't he do the calculation? I feel like it's
don't
not that
know.
hard.
Because
I feel like the calculation isn't that hard.
okay, but let me tell you his errors, though. Now here's why his calculation wasn't very exact. Because number one, those 11 minutes and 11 minutes that he added up to 22 minutes wasn't very accurate. Because of the orbits of the Earth and Jupiter, it was actually not 22 minutes, the total time interval. It was actually 16. So he was off by quite a big number, but somehow still got a very close number to the actual speed of light. But so these time intervals, plus I believe there was also an element of the orbital, the orbital, so the radius of the Earth, because they basically had to compare that time interval to the orbital radius of Earth, or the radius of Jupiter, or one of those things. There was some mathematical calculation that they were a little bit off on, and they didn't have the exact numbers. So I guess they just used approximations, and they came to this number that was a little off. So that's the reasoning. But again, what he did, this experiment isn't monumental because, wow, he found a speed of light. No. That's not why it's monumental. It's insane because he showed the world that the speed of light is not infinite. And the speed of light is not... Oh, also, I mean, this obviously kind of follows from what I was saying, but the time interval lengthening as he was moving away was exactly the same as the time interval shortening as he was going close. So that is how he also kind of concluded that it must be finite. It's not variable depending on which direction I'm going in, right? And that was a very important discovery that he also kind of implicitly made. Obviously, none of this was really like, oh, wow, we found this. This was all happened through decades and decades of research and calculations and stuff. But after all that, we finally had an idea for a finite speed of light. And I think the idea that poses is very interesting. Yeah.
Awesome. So I guess those are all the experiments we wanted to talk about today.
What about the Michaelson Morley? You think we can talk about the Michaelson Morley experiment?
I think we'll have to save that one for later.
Because I was talking about the speed of light. Anyway, so it has things to do directly with measuring the speed of light. But to be honest, I really love this episode. Let us know if you did as well, because I think I am quite inclined to make a part 2 of this episode. Sure. So let us know if you guys like this episode. I think, as I just said, I think Parker, you enjoyed it too. Hopefully, it was really cool, man. Like these experiments, some of these people are like, I mean, I hate to use the word genius first of all, but like these are very smart people. These are some very smart people because they thought completely outside of the box. Like they were light years outside of the box.
There are smart people in every epoch.
Yeah.
That come up with, whatever they can. Like I'm sure, like a person nowadays, if we were to transport them back to like the resources that someone has in the 1700s, they would be able to come up with some way of measuring the speed of light. But it's just they don't think about...
if we have the resources now and we send them back to 1700?
No, we send anyone, like just a smart person back then, they'd be able to come up with a way. It's just because nowadays they don't really think about measuring the speed of light because it's already known.
I don't know about that though, because in like the 15, 16, 1700s, like that was, to be honest, like those were like centuries of discovery and innovation where people literally had nothing else to do but, I guess go to libraries and just read books.
But if you tell them,
you
tell them measure the speed of light, they'll sit down and think about it.
You think someone from like a smart person from today?
Yeah, definitely.
I guess
definitely. If Einstein can come up with the things he's come
Einstein
up with,
is Einstein.
then,
like those are all like exceptions. But
I mean, they're just people.
I guess if we send Einstein back to 1700, I'm pretty sure he would be able to calculate the speed of light.
There are very smart people out here.
Yeah, that is true. And it's people like these that think about all of these, because experiments, they kind of go two ways, right? They can go one of two ways. Either you discover something experimentally, like you're doing something and you're like, oh, whoa, that's pretty cool. Let me go make a theory on it. Like there's that kind of experiment, and there's another experiment where you already have an understanding, you have a theory, and you're like, hey, let me test it with this experiment to see if it actually works. So those are like two kind of different types of experiments that we see, and I think both are equally like important, like in their own ways. Like if you see something really cool and you make a theory with that, I think that's a pretty interesting way to live life, For sure.
So if you did enjoy this episode, make sure to leave a like on YouTube and subscribe. Yeah. Also follow us wherever you're listening to this. Let's try to get to 10,000 followers. By when? When do you think?
10,000. Okay, so right now we're at 65, right?
Let's say August. By August, we'll have 10,000
March.
Followers.
April.
Actually, that might be too long. Maybe July.
Really? You think too long?
Yeah, I think July.
5 months. Yeah, I think 5 months. Yeah.
We had 2,000 followers in December, so if you do the math on that.
That is true, actually.
So leave a follow, leave a like, leave a whatever, and let us know.
Yeah.
Let us know how your day went. I don't know. Whatever you want.
Let us know.
This has been episode number 54 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.
See ya.